Hello everyone, welcome to this video on using eigenvalues to find the corresponding eigenvectors. So I'm assuming at this point that you know how to find the eigenvalues of a matrix A, or the spectrum of a matrix A, right, just the set of all the eigenvalues by solving the characteristic equation for that given matrix, right? Remember, that's the determinant of A minus lambda I, where I is the identity matrix. The determinant of A minus lambda I equals 0. You know how to solve this polynomial equation. Alright, so in this video, we're going to take those eigenvalues that you find by solving the characteristic equation, and then go back to the original equation that defines an eigenvalue and eigenvector, that A times vector x equals lambda times x, and find the solutions, the vectors x that will make that equation true for the given value of lambda. Alright, so we're going to be given eigenvalues and then go in and find the corresponding eigenvectors for that particular eigenvalue. Alright, so on the first page, I'm talking about eigenvectors and a vector space called an eigenspace that'll be related to every eigenvalue of a matrix. Right. And you've seen vector spaces plenty by now, I'm hoping, right? Null space, row space, column space, left null space, all that stuff of a matrix. You've seen plenty of examples of vector spaces before. This is just another one. Alright, so suppose we're given a square matrix A, right, say an n by n matrix A, and an eigenvalue of that matrix called lambda. Alright, the eigenvectors of A that correspond to this lambda are all of the non-zero vectors x, such that this statement holds true, such that A times the matrix times the vector is equal to the scalar lambda times the vector. Alright. But notice I underlined the word non-zero. Right, because obviously the zero vector would be a solution, right? A matrix times the zero vector, a scalar times the zero vector, both sides would give me the zero vector, and it would be a true statement. So that trivial solution, right, with just the zero vector as x is not interesting. So we're looking for non-zero solutions to this equation. Now another way to express this, remember in the last video on finding the eigenvalues, right, solving the characteristic equation, I rewrote this side with the lambda x as lambda times I times x, where I is the the identity matrix, right, the same size as A, so it would be the n by n identity matrix. The only reason that was introduced is so I could actually do some subtraction of matrices, because in order to subtract matrices, remember, they have to be the same size. So if I make this lambda times Ix and subtract and then factor the x out, remember matrix multiplication is distributive over matrix addition. I factor the x, the x is on the right side of both of these expressions, so I factor it out on the right. We get this equation here, which is again equivalent to this one. The matrix A minus lambda I, this matrix, times x equals the zero vector. And we'll be looking for, what vectors can I replace x with to make this true for the given value of lambda. And those, the non-zero vectors that I can replace this with and make this true are the eigenvectors of the matrix corresponding to the given value of lambda. All right, lots of fancy words, lots of symbols, I know. Bear with me, we'll get to some examples shortly. Now, the set of all the solutions x, all the x's that I can replace this with, including the 0 vector. So all the eigenvectors along with the 0 vector, which is not an eigenvector. So all the solutions of this equation make up a vector space. If you look at all possible solutions, including the 0 vector, make up a vector space. This vector space is given the name the eigenspace of lambda, right, of the particular eigenvalue we're working with. So another way of saying this is that the eigenspace of lambda is all the solutions of this equation. Well, if I find solutions to this equation here, I'm basically finding the null space of this matrix A minus lambda A, right? Remember, the null space of a matrix was all the vectors that you could multiply that matrix by to get the 0 vector. That's exactly what's happening here. Alright, so I've written that out on the next page. Alright, so the eigenspace of an eigenvalue lambda is the null space of the matrix A minus lambda I. Right, I've written that here in a nice little box. Right? The eigenspace of lambda equals the null space of A minus lambda I. Great. Alright, so what I'm doing for the rest of the video is I have these examples of square matrices, and I have written their spectra. Right? Remember, the spectrum is just the set of all the eigenvalues, right? The solutions to that characteristic equation from the last video I made. So you can verify these if you wish, and in fact the first 2 or 3 examples I have are some of the same matrices I worked with in the last video where I had to find the spectrum. So if you'd like to go back and watch that, you can. But so here we're given some square matrix A, and what I'm asked to do is find the eigenvectors corresponding to the eigenvalues, right? So here's a matrix A, 2 by 2, with columns -2, 1, -7, 6. And I've already verified this, right? You can check on your own, find the eigenvalues on your own if you want to verify this for yourself. This matrix has a spectrum, right? The spectrum of A is just a set with -1 and 5, so the eigenvalues of A are -1 and 5. So for the first part, I'm going to find the eigenvectors corresponding to -1, right? You can only really work with one eigenvalue at a time. Right. So find the eigenvectors corresponding to lambda equals -1. Alright, in order to do this, we're going to be solving, well, I don't know why I put step 1 there. This is the only thing you're doing. You're solving that equation from earlier, A minus lambda I times, some vector x equals the 0 vector. All right. You're solving for x. Now, again, lambda is given. All right, so this matrix here is now, instead of A, I'm replacing lambda with -1. So this is A, minus -1 times I, so A plus I. A plus 1I times vector x, equals the 0 vector. And if you want to write these out as matrices, when you subtract lambda I from A, you're simply subtracting whatever lambda is from the main diagonals, the main diagonal entries of A. And all the other entries that aren't on the main diagonal stay the way they are. So A plus I, or A minus -1I, is the matrix, it's the 2 by 2 matrix, where down the main diagonal, I'm just adding 1 to the main diagonal. So that'd be -1, +5. Right? And then the other entries that aren't on the main diagonal, negative 7 and 1, stay the way they are. Negative 7, positive 1. Okay. Sorry, this should be 7. I was just looking at this, and this doesn't have a determinant of 0, but I said add 1, didn't I? Negative 1, 6 plus 1 is 7. I added negative 1. Sorry, minus negative 1 plus 1. So plus 1 down the main diagonal. My apologies for that. So that's a 7 there. So negative 1, negative 7, positive 1, positive 7. Times, and then vector x. All right, now the vector x would have to be a 2 by 1 vector. So let's say it has components x1 and x2. And I want this to be equal to the 0 vector, which would again be the 2 by 1 0 vector, right? The 0 vector from R2. Right. Okay, and then hopefully this looks familiar, right? This is actually like a system of equations involving this x1 and x2. And you could set up an augmented matrix where the first column here is the coefficients of x1. The second column represents coefficients of x2. And I'll do that here on the next page. So I set up the augmented matrix where, again, just remember these are coefficients of x1, coefficients of x2, and a little equal sign, the bar, and then zeros on the other side. And remember solving these, right? You've seen plenty of videos now, hopefully. You've seen, at least in your reading and doing examples, plenty of problems where you had to take a matrix and put it into some echelon form, whether it be echelon form or reduced echelon form, and solve the system. I personally prefer reduced echelon form, reduced row echelon form. RREF on your calculators sometimes, right? To solve, and then sometimes too. In the first example, I will write the column of zeros here, but just know that you're always going to have this column of zeros when solving this equation, right? This is a homogeneous equation. You always have zeros over here, and when you perform row operations, any column of zeros will stay a column of zeros. So very often I'm just going to not write this and imagine that it's there. All right, so I put this matrix into reduced row echelon form, which would be very simple in this case. All I would need to do is, you see how these, this first non-zero entry here, this pivot point is -1. This is all I would need to do is add the first row to the second row, and that would make the second row a row of entirely of zeros. And then the first row, right, in order to be in reduced row echelon form, I need that first non-zero entry to be a +1. So I would simply multiply the top row by -1, making this +1, this +7, and again, this column of zeros will remain a column of zeros. So here we have it, right? Every row, the first non-zero entry is a 1 with zeros above and below it, and all rows that are made fully of zeros are at the bottom. This is in reduced echelon form, and then I can use this to find solutions to this equation, right? So from the first row there, look at your pivots, right? This is a pivot, those leading non-zero ones in any row. And then, so the first column is a pivot column, meaning that my first variable, the x1 that I put up here, is a basic variable, right? And then the second column does not have a pivot, right? It doesn't have one of those leading ones in it. So x2 is what they call a free variable. I can replace x2 with any number I wish, any real number I want, and then find x1. Now you've seen me in past videos. I personally like to replace free variables with other parameters. You can leave x2 as x2 if you wish, but I'm going to say let's let x2, I'm going to replace x2 with the variable t, where t is any real number. Right? Just so long as you're replacing your free variables with an expression that can take on any real number value. Alright, then, in the first row, in reduced echelon form here, we're seeing 1x1, so x1, plus 7x2, so plus 7t must be equal to 0. And solving this for x1, we'd see that the value of x1 must be equal to negative 7 times t. So the solutions to this equation look like this. The solutions are these vectors x, which again have two components, x1 and x2. And we're seeing that x1 is to take on this expression is negative 7 times my choice of whatever value I want to replace t with, and x2 is the free variable t. And do you notice how each of these has this free variable parameter t in it? Let me pull that out. That's like a scalar, and times the vector negative 7, 1. Right. So all of these here make up what's called the eigenspace of lambda equals negative 1. Alright, so let me write that. The eigenspace of negative 1. Right, I'll say, now usually I would just put the number negative 1 in there, but of lambda equals negative 1, this particular eigenvalue is the set of all vectors that look like this, right? Again, every solution to this equation, even the zero solution. So all the vectors that look, every vector that looks like this, some scalar t times the vector negative 7, 1, so long as t is real. Remember, another way you could write this is that this is the span of the vector negative 7, 1 of the set with the vector negative 7, 1. Right, all scalar multiples of that. So that's big. Right? That is a vector space. Right, now that's not all. Not every vector in here is an eigenvector. Remember, eigenvectors are non-zero. So I would simply just say t can't be 0. If we're talking about the eigenvectors corresponding to negative 1, which I'll get to in a second. Another thing to point out, the dimension, right, the dimension of the eigenspace of negative 1, right, this has a dimension of 1, right, because this set with one vector would form a basis for this space. So I'll point that out as well, right. It is a vector space. It should have a dimension as well. It has a dimension of 1. Okay. Alright, so I've got the eigenspace for lambda equals negative 1. What about the eigenvectors? Again, like I said, the eigenvectors are just all these solutions, just not the 0 vector. Right? This set has the 0 vector in it. The eigenvectors can't be 0 vectors. They have to be non-zero vectors. Right, so the eigenvectors corresponding to lambda equals negative 1, or sorry, the eigenvectors of A, right, of matrix A, corresponding to lambda equals negative 1, corresponding to that eigenvalue, are the set of these vectors t times some scalar t times negative 7, the vector negative 7, 1, as long as t is not 0. Right, as long as t is not 0. this is finally what I was asked for, right? Find the eigenvectors. Now, in a lot of texts, they'll say, find the eigenvector corresponding to lambda equals -1. Just know that there are going to be, there are infinitely many eigenvectors corresponding to lambda equals -1. But when they talk about what are the eigenvectors, really just the eigenvectors that form a basis for the eigenspace is what they're really asking for. So, they may say, right, so from this, they may say that just the vector -7, 1 is, the eigenvector of A corresponding to lambda equals -1. They might say that, and you might be asked for just one of them, or just, but just know that when this is said, it's implied, or it should be understood, that not only this one is an eigenvector corresponding to this value, but any scalar multiple of it, right? As long as it's not the zero vector, right? Any non-zero multiple of that. And let me show you. All right, let's see if these actually satisfy that. Remember the definition of eigenvector, eigenvalue, eigenpair. So let me demonstrate this here. So, -1, obviously this would be an eigenpair. And we can test that out. If I take matrix A, right, going back to what matrix A was. So if I take matrix A, -2, -7, 1, 6, and multiply it by the vector -7, 1, that should be equal to -1 times the vector -7, 1. This should be true. And you can check that, right? Now, if I multiply these two, see, I'd have 14, I get a 2 by 1, where the first row, first column would be 14 minus 7, or +7. And that's -1 times -7, so that's correct. And then the second row, first column would be -7 plus 6, or -1, which is -1 times 1. So this is true. But as I was saying, not only is this an eigenvector corresponding to -1, but we see up here, any non-zero multiple of this would also be an eigenvector corresponding to -1. So you could have -1 and then say 3 times this, which would be the vector -21, 3. This is another eigenpair. And you can double check. Let's do it. Take matrix A, -2, -7, 1, 6 here. Multiply it by -21, 3, and what I get as a result should be -1 times that same vector times -21 and 3. And let's check this, right? I'd have over here, if I multiply these two, the first row, first column would be, +42 minus 21 would be +21. And over here, first row, first column would be +21, -1 times -21. Then second row, first column would be -21 plus 18 would be -3. Over here, -3, right? So, and so on, right? I could do this all day long, right? Many more, infinitely many more. All right. Okay, so when you're asked, find the eigenvector that corresponds to a given eigenvalue, your answer could be different from what they have in the back of the book or something, right? Because there are infinitely many possibilities. I just replace t with some non-zero number, and I've got another one. Okay, but usually, if you go through and solve your system, solve your equation, that vector that ends up being multiplied by the free variables, those vectors usually are what they're talking about. Right, the vectors that form a basis for the eigenspace. Okay, so that was for that was for -1, right? That was for -1. So I'm going to do the next one a little faster, because notice, that -1 wasn't the only eigenvalue of A, so is 5. All right, so let's do the same thing. I'm going to find the eigenspace of 5, and also, then the eigenvectors corresponding to 5, which is, again, just the eigenspace without the 0 vector, right? Just get rid of the 0 vector, and then you have your eigenvectors. All right, so same matrix A, right, but now we're going to find eigenvectors corresponding to lambda equals 5, right, to that eigenvalue. All right, so same thing, I'm solving this equation. A minus lambda I times, some vector x, and I'm trying to find these vectors x, that would give me the 0 vector. So this is A minus 5I times x equals the 0 vector, right? I'm replacing lambda with 5 this time. Okay. And I can write this as a nice matrix equation. What's A minus 5I? So again, I'm just subtracting 5 from the main diagonal entries of A. So -2 minus 5, hopefully I do it right this time, -7. 6 minus 5 is 1. All right. And then the other entries, the non-main diagonal entries, stay the same. -7, 1. Then multiplied by, again, my vector. Again, this is a 2 by 2, so my vector would be a 2 by 1 column vector here. I have two components, say x1 and x2. And I want this to be equal to the 0 vector. Alright, and so the same thing, I'm going to set up my augmented matrix. Just remember, my first column is coefficients of x1 and my second column coefficients of x2. So -7, 1, -7, 1, little bar where the equals would go, and then 0, 0. And as I said, after this first example on this matrix A, I'm going to stop writing the column of zeros and just imagine that they are there. Alright, now this is another pretty simple one to put into reduced row echelon form. Do you see if I just multiplied the top row by 1/7, you'd have -1, -1. Then if I add that to the bottom row, that would get rid of the bottom row. The bottom row would be made up entirely of zeros. And then to get it in reduced row echelon form, have that leading non-zero entry in the first row be a +1. I multiply the top row by -1/7, which will make that a 1 and that a 1. And then again, always a column of zeros here on the right side of the bar. Alright. And then I just look for my pivots in here. Same thing, right? Pivot in the first column. So again, x1 is a basic variable. And the second column is not a pivot column. Right, so x2 is again a free variable. And as with all my free variables, I'm going to replace that with something. So I'm going to say let x2 be replaced by the letter t, right, where t is any real number. All right, and then from the only row, this second row says 0 equals 0. That's fine. The only row that's given us any information is all is the first row, which is telling me 1x1 plus 1x2, so plus 1t is equal to the number 0. And then solving this for x1, we're seeing that x1 must be the opposite of t. All right, so then I can write out the solutions and therefore describe the eigenspace. Right? If I write out all the solutions of this, I'll describe the eigenspace of the eigenvalue 5. So the solutions of this equation are vectors x that have two components, where the first component x1 is the opposite of some t that I choose, and the second component x2 is just the t that I choose. And each of these has the variable t in common. Pull that out, and I have t times negative 1, 1. All right. So what I have here is a description of all the solutions, even the zero vector, right? Even though the zero vector is not an eigenvector, right? Eigenvectors have to be non-zero. But what I have described here is the eigenspace. Right? The eigenspace of lambda equals 5, right? Or just 5 there. The is the span of this vector negative 1, 1, right? The set with the vector negative 1, 1. Every single scalar multiple of negative 1, 1 is a solution of this equation, this a minus 5i times x equals 0. So here I have the eigenspace, and again its dimension would be 1. Right? This particular vector space would have dimension 1. Right? It has because obviously this set with this one vector would be a basis for it. All right. This can change. I mean, not every eigenspace has a dimension of 1, as we'll see hopefully later in the video. Okay, and then the eigenvectors. Right, the eigenvectors of A corresponding to lambda equals 5 are the following. They're the set of all the vectors that look like this, but just not the zero vector. Right? All the vectors that are multiples of negative 1, 1, but just so long as t is not 0. Right? Just not including the zero vector. Right, and this is what I was asked for here to do. All right, now like I said, in some texts they'll ask you for what's the eigenvector of A corresponding to lambda equals 5. Just use the vector negative 1, 1 then. That's fine, right? So let's test that out, right? Let's test that out. Is this an eigenpair? The lambda 5, the number 5, and the vector negative 1, 1. This should be an eigenpair of matrix A. All right, and let's test it. So again, going back to matrix A. All right, this I'll just write it here. Right. So we have negative 2, 1 first column, negative 7, 6 for the second column, and then multiplied by the vector negative 1, 1, and this should give me 5 times that vector, right? Or negative 5, 5. And double check, you have 2 minus 7, negative 5 for that first component, great. Then negative 1 plus 6, positive 5 for the second component, great. It works, right? But that's not the only one, right? Like I said, you could pair 5 with any multiple of this, negative 2, 2, 5, negative 5, negative 10, 10, whatever you want. And that will be another eigenpair of A, give you another eigenvector corresponding to the eigenvalue of 5 for this particular matrix. Okay. All right, so that was for that example. Let me do it again here. Alright, so I'm going to do one more 2 by 2 example, and then a 3 by 3. Alright, and I'll do a 3 by 3 that I didn't do in the last video, right? Just to be a little different. Alright, so the next one this is another 2 by 2 that I had in the last video I did, where I found the eigenvalues. And so this 2 by 2 matrix has spectrum. The spectrum of A is the set with -6 and 5 in it. Right, so -6 is an eigenvalue of A, and 5 is an eigenvalue of A as well. And just like last example, I'm going to go first. Let's find the eigenvectors corresponding to the eigenvalue of -6. So I'm just going to say the eigenvectors of lambda equals -6. So just know that I mean corresponding to lambda equals -6. Right? So this time we're solving this equation. Right? So remember, it's A minus lambda I. This time lambda, though, is -6. So A minus -6i or plus 6i times, some vector x that I'm trying to find. I'm trying to find these vectors that I can plug in to give me the 0 vector. All right. And I'll write this as a little matrix equation. What's A plus 6i? Now, A plus 6i is simply add 6 to the main diagonal entries. So this, again, this 2 by 2. If I add 6 to the main diagonals, I get 4 plus 6 is 10. -5 plus 6 is 1. And then the non-main diagonal entries stay the same. So -1 is still there, -10 is still there. It's a 2 by 2, so again the vector x would be a vector with 2 components, say x1 and x2 again. And I wish this to be equal to the 0 vector, right? With, again, 2 components, 0, 0. Alright, so this time I'm going to just take this matrix. Remember how I wrote the augmented matrix with the bar and then the column of zeros? This matrix, then a bar, then a column of zeros, and then put that into reduced row echelon form. I'm not doing that this time. I'm going to just ignore that column of zeros. Just imagine that they're there, though, still. Alright. I'm just going to straight up put this matrix into reduced row echelon form now. Right. Now again, it's only a 2 by 2, and it's very easy, this one. If I put this into, can you see how the first row and second row, if I just add them together, the second row, if I add the first row to the second row will be gone, right? It will just be zeros. And you've probably noticed that in all the examples so far. I ended up with a row of zeros at the bottom, and you should, right? And then the top, in order to put it into reduced row echelon form, I want that first non-zero entry in the row to be a 1. So I'd multiply the top row by 1/10, making this a 1 and this -1/10. And again, don't forget, we're imagining a bar here with some zeros. Right, this is x1 minus 1/10 x2 equals 0. This is 0 equals 0. Alright, looking for the pivots. Again, upper left corner there, leading 1 pivot in the first column that corresponded to coefficients of x1. So again, x1 is basic, and again, x2 is free. Now, you can do what I've been doing, say let x2 equal t, but I'm going to do something a little different here because of the fraction. Now, if you want to let x2 be t or just keep x2 as x2, that's fine. Nothing wrong with that. I just want to get rid of the fraction. So if I replace x2, this is going to be -1/10 times x2. I'm going to replace x2 with something that has a multiple of 10 in it, so the 10s will cancel, and it'll be nicer looking for me. So instead of having x2 be just t, I'm going to have x2 be 10t, where t is any real number. right? And 10 times t can be any real number you want as well. Just make sure the expression you replace your free variables with can take on any real number value. All right, so if I do that, then we get the following, right? The first row would imply that x1 plus, negative 1/10 x2. So that'd be minus 1/10 times 10t. And do you see how the 10s would cancel? I'm not writing it. But negative 1/10 times 10t would just be negative 1t. And that's the whole reason I made this 10t, is so that the fraction would go away. And this, again, imagine you know that the equal 0's got to be there. Right? This needs to be equal 0. So x1 would have to be t. All right, and so our solutions here, right, so the solutions to this equation, this a plus 6i times x equals 0, the vectors I replace x with will have to look like this, where the first component, x1, is just some value of t that I'm choosing, and the second value, x2, is 10 times that value of t I choose. And if you'd like, pull the t out, and you have the vector 110. All multiples of vector 110 are solutions of this equation. All right, so what I have there, right, a description of all the solutions of the equation, that's the eigenspace of lambda equals -6 of that eigenvalue. Right. So the eigenspace of just lambda equals 6 is this just all the scalar multiples. Any scalar contains any scalar multiple of the vector 110. So that's the span of the set with the vector 110 in it. And yet again, I have an eigenspace with a dimension of 1. Right, because this set with the vector 110 in it is clearly a basis for this vector space. So again, this has a dimension of 1. Right. And then the eigenvectors of this matrix that correspond to, -6, sorry. I wrote 6 here, -6, lambda equals -6. Then the eigenvectors are just the eigenspace vectors, all the vectors in the eigenspace, but without the 0 vector. So just all these vectors that look like this, just so long as t is not 0. All right, so the eigenvectors of A, I'll say 4, corresponding to lambda equals -6, is the set of these vectors, all the vectors that are multiples of the vector 110, just so long as you don't have the 0 vector. Right. All right. And you can double check this, take the matrix. I'm not going to write this out this time, but take the matrix and multiply it by 110. And then your output should be the same as -6 times the vector 110, right? The -6 and the vector 110 are an eigenpair of matrix A. But not only that, -6 and 220, or 1/2 5, or 1/3 10/3. Just any multiple of 110 with -6 will also be an eigenpair, will also satisfy the equation in question. Great. All right. So that was for -6, and I'm going to do the same for 5 real quick. So let's find the eigenvectors for lambda equals 5, the other eigenvalue of this matrix. So again, I'm solving the following equation. A minus lambda I, right? A minus 5I, right? Replacing lambda with 5 times some vector x equals the 0 vector, right? I'm trying to find all these vectors x. All right, A minus 5I is simply take matrix A and subtract 5 from the main diagonal entries. Right, so I have 4 minus 5, negative 1, negative 5 minus 5, negative 10 for the main diagonal, and then the non-main diagonal entries stay the same. Negative 1 here, negative 10 there. Vector x, again, this is a 2 by 2, so the vector x would have two components, say x1, x2. And we want this to be equal to the 0 vector again. Right, and as with the last part of this example, when we did with lambda equals negative 6, instead of writing like an augmented matrix with a bar and a column of zeros, I'm just going to put this matrix here into reduced row echelon form and imagine that there's that column of zeros on the other side. All right. Once again, pretty simple. If I just take negative 10 times the first row and add it to the second row will disappear and become a bunch of zeros. And to get the reduced row echelon form, I need the leading non-zero entry in the first row to be a 1, so I just simply multiply by negative 1, making each of those a 1. Alright, so pivots, this is the only pivot position. So x1 is again basic, x2 is again free, and I'm going to replace x2 with just t this time, or there's no fractions here this time, where t is any real number. And then from that first row, again, you're imagining that the equal zeros over there, right? We're seeing that x1 plus x2, so plus t, must be equal to 0, meaning that x1 must be the opposite of t. And putting this all together, our solutions of this equation, the a minus 5I times x equals 0, the vectors x have to look like this. You know, the first component, x1, is the opposite of my choice of t. The second component, x2, is my choice of t, and pulling the t out in t times the vector negative 1, 1. All right. So we have the eigenspace is again all the solutions, including the 0 vector. Right? And remember that the 0 vector is not an eigenvector. But the eigenspace of lambda equals 5 is the span of the vector, the set with the vector negative 1, 1. Right? It's all the multiples, all scalar multiples of the vector negative 1, 1. And yet again, we have an eigenspace here with a dimension of 1, right? This set with the vector negative 1 and 1 in it clearly forms a basis for this vector space. Let's say dim equals 1. Now, and I know you're probably thinking, hey, does every eigenspace have a dimension of 1? No. Right? My last example in the video, we'll see an eigenspace that has a dimension of 2. All right, and it can have really any dimension up until the multiplicity of the eigenvalue, which I'm not going to get into. Right? We talked about multiplicity of eigenvalues last video. Yeah, and then the eigenvectors corresponding to lambda equals 5 are just all of these multiples of negative 1, 1, just not the 0 vector. Right, so I wouldn't want the value of t to be 0. So then the eigenvectors corresponding to lambda equals 5 here are all the multiples of the vector negative 1, 1, just so long as that you don't have the 0 vector in there, right? That t is not 0. And you can double check. Take whatever matrix A was, multiply it by negative 1, 1, the vector, and you'll get 5 times this. You'll get negative 5, 5 back. So 5 and negative 1, 1 form an eigenpair. 5 and negative 2, 2 form an eigenpair of A. 5 and 10, negative 10. Just any multiple of this along with the number 5 form an eigenpair of matrix A, and you can double check that. Okay, so that was for some 2 by, my first couple examples were involving 2 by 2 matrices. My last example involves a 3 by 3. Now, a 2 by 2 matrix is going to have up to 2 distinct eigenvalues. And you saw the last 2 examples, that both those 2 by 2 matrices had 2 distinct eigenvalues. And a 3 by 3 matrix is going to have up to 3, and a 4 by 4 is going to have up to 4. Doesn't mean they're going to have 4 or have 3, but up to that many distinct eigenvalues. So here's a matrix, 3 by 3, at 0, negative 4, negative 6, negative 1, 0, negative 3, 1, 2, 5, okay. And you can verify this on your own, right? Set up the characteristic equation and solve and find the eigenvalues. This has eigenvalues of just 1 and 2. So notice it only has 2 eigenvalues, but it's a 3 by 3. And that's fine, all right? It doesn't have to have 3 just because it's a 3 by 3. What actually happened here is, and again, you can verify this on your own, but the multiplicity of 1 in that characteristic equation was 1. And there's actually a repeated root, a repeated solution in the characteristic equation. This has a multiplicity, the number 2 actually has a multiplicity of 2. And again, I ask you to verify this on your own. Set up the characteristic equation, and you'll eventually end up seeing that 1 has a multiplicity of, the number 1 has a multiplicity of 1, and the number 2 has a multiplicity of 2. And it's not just because they're the number 1 and the number 2, right? Other numbers can have multiplicities of 1 and 2. But just, again, I ask you to verify that on your own. All right, what I'm here to do now is find the eigenvectors, right, corresponding to these eigenvalues. All right, so how about for lambda equals 1? So again, we're solving this equation. A minus lambda I, so lambda's 1 this time, so just A minus I times some vector x, when is this equal to the 0 vector? Alright, now A minus I, this is just, negative 1i, so I'm just subtracting 1 only down the main diagonal entries. So it's a 3 by 3, where 0 minus 1, negative 1. 0 minus 1, negative 1, and then 5 minus 1, 4, and then all the other non-main diagonal entries stay the same. So negative 4, negative 6, negative 1, negative 3, 1, and 2. And my vectors this time, this is a 3 by 3, so it would have to have 3 components. So let's say components with variables x1, x2, x3. Or xyz if you want, I don't care. Right? Just 3 unknowns. And then we wish this to be equal to the three component 0 vector, right? The 0 vector from R3. Alright, just remember these are coefficients of x1 down here, coefficients of x2, coefficients of x3 for each column, right? Alright, and then just as before, I would like to put this, you could write the augmented matrix with a bar and then some column of zeros, right? But I'm just going to stick with the 3 by 3 here and put this into reduced row echelon form. Now this time I'm going to go to the calculator. Alright, put in a 3 by 3. My 84 plus over here. So go to the matrix menu, over to edit. It's a 3 row, 3 column matrix, and I enter these entries, negative 1, negative 4, negative 6, negative 1, negative 1, negative 3, 1, 2, and 4. Right. Okay, I've got the entries entered. I get out of there, go back over to math, scroll to RREF. Again, please don't confuse this with REF. That's row echelon form or just plain echelon form. I want reduced row echelon form here. And then what matrix? So back to the matrix. Matrix A, please. Right. Okay, so here it is. Again, notice how there's that, there's going to be at least one row of zeros in these, because remember the eigenvalues of a matrix are the numbers of lambda that when you plug it into A minus lambda I, the resulting matrix has a determinant of 0. So when you put it into an echelon form, you should have rows of zeros showing up. That's not a mistake. All right. So I'm going to write it out here. So we have down the first column 1, 0, 0. Down the second column 0, 1, 0. And the third column 2, 1, 0. Now remember, I'm imagining that there's this equal 0, equals 0, equals 0 on the other side. So now I'm looking at this for pivots, right? Those leading non-zero those leading entries, those leading ones. There's a pivot there and a pivot there, right? Those leading ones down each row. So looks like x1 and x2 are basic in this case, right? They correspond to pivot columns. x3, right? The third column here doesn't have one of those pivots in it. So x3 is free. And as with all my other ones, I'm going to let x3 be replaced by the letter t, where t is any real number I wish, right? Alright, so now I got 2 rows to contend with here that actually have some non-zero entries, right? The third row just tells me 0 equals 0, which is fine. That is a true statement. Alright, so from the first row, I'm seeing that, x1 plus 2x3, right? No x2, 2x3, or 2t must be equal to 0, telling me that x1 will be equal to negative 2 times t. And then the second row is no x1, 1x2, so x2 plus 1x3, so plus 1t equals 0. And then solving this for x2 gives me x2 equals negative 1t. All right. And then putting all this together on the next page, we see our solutions to this equation. Right? The solutions to this a minus I times x equals 0 look like the following. I can replace the vector x with, and it's going to have 3 components, where the first component is negative 2 times that free variable t, the second component x2 is negative 1 times t, and the third component is just t. And pulling the t out, I have the vector, t times the vector negative 2, negative 1, 1. And there we go. There's a description of all the solutions of this equation, including the 0 vector. Alright, so this is a description of the eigenspace for lambda equals 1. Right? So the eigenspace for lambda equals 1 is just the span of the set with this vector negative 2, negative 1, 1 in it. And yet again, and I know, this has a dimension of 1, right? This set with the 1 vector forms a basis clearly for this vector space. The dimension equals 1. Right? And then all the eigenvectors of A corresponding to 1, lambda equals 1, are just the non-zero, all of these without the 0 vector. So every multiple of negative 2, negative 1, 1 there without the 0 vector. All right, so the eigenvectors is the set of all the vectors that look like this, some multiple of -2, -1, 1. Just so long as you're not including the 0 vector, right? The 0 vector is not an eigenvector. I'll say that a bunch of times, right? You've heard me say it already. All right, so that means that if you take matrix A, multiply it by -2, -1, 1, you're going to get -2, -1, 1 back, right? Because it's equal to 1 times that vector. So if you multiply matrix A by any multiple of this, -4, -2, 2, -6, -3, 3, whatever, you're just going to get that vector 1 times that vector as an output. You're just going to get that vector back. Okay. Wonderful. All right. Now finally, the last of these. So that was for lambda equals 1. Right? We found the corresponding eigenvectors right down here, corresponding to lambda equals 1. All these multiples of -2, -1, 1. Let's do the same thing for 2 now. Now, so far, hopefully you've noticed that every single eigenvalue with a multiplicity of 1, right, I mentioned all the other ones that are multiplicity of 1, had an eigenspace with a dimension of 1. The dimension of an eigenspace for an eigenvalue will be less than or equal to the multiplicity. All right. In fact, I'll write that little note over here. All right. The dimension of an eigenspace, right, the dimension of the eigenspace of an eigenvalue, say the eigenspace of lambda, will be less than or equal to the multiplicity of that eigenvalue in the characteristic equation. Right? Right. So when I go and find the eigenvalues, or the eigenvectors corresponding to 2, and I told you it has a multiplicity of 2, the dimension of the eigenspace is either going to be 2 or 1. Right. It's going to be 2 or less. So let's see what happens. All right, so for lambda equals 2, and same stuff, I'm going to be solving the following equation. A minus lambda I, this time lambda is 2, A minus 2I, that matrix times, some vectors x. When's this equal to the 0 vector? All right, now A minus 2I is simply matrix A with, you're subtracting 2 down the main diagonal entries. So -2, 0 minus 2, 0 minus 2, 5 minus 2. And those 3 there. And then every other entry is the same. -4, -6, -1, -3, then 1 and 2. Times, and then, okay. The vector is going to have 3 components. Let's again say they're x1, x2, and x3. And we wish this to be equal to the 0 vector from R3, right, with 3 components. Okay. All right, take the matrix A minus 2I, put this into reduced row echelon form. Now this one's real simple. I don't need to go to a calculator for this one. You see how look at this the third row. See how the third row is just the opposite of the second row? So if I add the third row to the second row is full of zeros. And if I just double the third row and add to the first row is full of zeros. And then I'll just move the first row up top, put those 2 rows of zeros on the bottom. And again, you can go to the calculator for this if you wish, but it's just going to be 1, 2, 3, and then a couple rows of zeros. Okay. And you can verify that and go to the calculator if you want. Now again, you're imagining the equals 0 equals 0 equals 0 over here. Alright, now I've got it in reduced echelon form. I look for the pivots. Well, there's only one pivot this time. Alright, there's a leading one in the first row, and then the second row doesn't have a pivot, the third row doesn't have a pivot. Alright, so then your pivot columns, the first one does, and this corresponds to coefficients of x1. So x1 is basic, but look, this time there are two free variables, right? So far, we've only seen examples where there's been one free variable, right? And the dimension of the eigenspace was 1. The number of free variables will be the dimension of the eigenspace, right? Just like the number of free variables was the dimension of the null space of a matrix in videos past. So x2 and x3 are free, right? Now there's two of them, so I gotta make two different assignments. I'm gonna let x2 be replaced by the letter s, right? Where s is any real number, and x3 be replaced by the letter t, right? Where s and t belong to the reals, right? They're any real number I wish. And again, there's no fractions, so I didn't use any other numbers besides just one s and one t. All right, and then from the first, the only row that means anything. This is the second row and third row both say 0 equals 0, which is totally fine. The first row is telling me that x1 plus 2x2, so plus 2s, plus 3x3, so plus 3t, must be equal to 0. And I solve this for x1, right? So x1 must be equal to negative 2s and then minus 3t. Right, so now I have each of the variables, x1, x2, and x3, in terms of these parameters, s and t, these free variables, s and t. Alright, so now I can describe the solutions of this equation, this a minus 2y times x equals 0 down here. So every vector I replace x with that makes this true, and we'll have three components where the first component is negative 2s minus 3t, second component is just s, and the third component is just t. Now, you've probably seen something like this before, I'm sure, when we talked about null space, especially of a matrix. Two free variables. So I could split this vector up into the sum of two vectors, one involving s and one involving t. So the one with the s terms going, this is the vector negative 2s, and there's 1s, and then 0s in the third component, right? Plus, and then the ones involving t, there's negative 3t in the first component, 0t in the second component, so it is 0, and then 1t in the third component. And then these I can pull an s out of, these I can pull a t out of. So we have s times the vector negative 2, 1, 0, plus t times the vector negative 3, 0, 1. And do you see how every solution of this equation is a linear combination of the vectors negative 2, 1, 0 and negative 3, 0, 1? In other words, and again, this is including the 0 vector, right? If I replace s and t with 0 and 0, I'd get the 0 vector as a solution, but that's not an eigenvector. But this describes all the solutions of that equation, and all the solutions of that equation form the eigenspace for lambda equals 2. Right, so the eigenspace for lambda equals 2 is just the set of all linear combinations of these two vectors. So the span of the set with just the vectors, with the vectors negative 2, 1, 0 and the vector negative 3, 0, 1 in it. And notice that this has a dimension of 2, right? This set with two vectors clearly forms a basis for this space. This has a dimension of 2, which again, the dimension, as I mentioned on a previous page, the dimension of an eigenspace for a particular eigenvalue is going to be less than or equal to the multiplicity of that eigenvalue, which here it's equal, right? I told you the multiplicity of 2 of lambda equals 2. I told you the multiplicity was 2, and this has a dimension of 2. It could have had a dimension of 1. You'll see other examples in your work, in your practice, where an eigenvalue has a multiplicity of 3, let's say, and the dimension of the eigenspace is 2 or 1. I mean, that can happen. Right? It's less than or equal. All right, so we got that. And then the eigenvectors are just all of these without the 0 vector, right? The eigenvectors corresponding to lambda equals 2 are basically the set of all vectors that are just any linear combination of the vector -2, 1, 0 and -3, 0, 1, just so long as both s and t are not 0. S is not 0 and t is not 0 at the same time. Now, one of them can be 0 and the other one not be, right? Just that both s is not 0 and t is not 0. Right. I guess another way you could just say that is that either, s is 0 and not 0, or t is not 0. But they both can't be 0. So you could say or s is not 0 or t is not 0. And as long as one of those is true, you're okay. Or both of them. But if both of them are false, then they're both 0, then you got the 0 vector. That's bad. Right. Okay. And and I'll circle this, right? This is what we were asked for. Now let's test this out, right? Let's test this out. So what they would say is, when they say like find the eigenvectors corresponding to lambda equals 2, they'd want -2, 1, 0 here and -3, 0, 1. Right? -2, 1, 0, and they'd want both of these, right? Again, like I said, just whatever vectors form a basis for the eigenspace. Right, when they ask for the vectors, the eigenvectors corresponding to a particular eigenvalue, just give a couple. Just give some vectors that form a basis for the eigenspace, and you'll be fine. All right, and you can check this. Take matrix A. I'm not going to write this out this time, but if I took matrix A and multiplied it by -2, 1, 0. I should get -4, 2, 0. I'd get 2 times that back. If I took matrix A and multiplied it by -3, 0, 1, I would get 2 times that back, -6, 0, 2. If I added these together, again, take any linear combination of them. If I were to add these together, I get -5, 1, 1. If you took -5, 1, 1, multiplied it by matrix A, you'd get 2 times -5, 1, 1 back, -10, 2, 2. Right. And replace s and t with any numbers you wish, as long as they're not both 0. All right, as long as they're not both 0. So in fact, let me cross off this. This is actually just a better way of saying this. Is a better way of saying this. All right. So as long as they're not both 0. All right. So one is not 0, or the other one is not, or both are not 0. All right. So you could have this one be 5, that one be 0. This one be 10, that one be 0. This one be 2, that one be 3, and you're totally fine. All right. Just so long as s is not 0 and t is not 0 at the same time. They're not both equal to 0. Okay, and check it out. And multiply whatever you get, multiply it by matrix A, and your final result should be 2 times that, right? The lambda is 2. All right, wonderful. All right, so a lot of stuff there, a lot of stuff going on. Eigenspaces, eigenvectors, right? Just the eigenspace without the 0 vector. You're solving that equation a minus lambda I times x equals 0. You're finding the x's. And it's just like finding the null space of a minus lambda I, right? The null space of that matrix. And just, for the eigenvectors, just exclude the 0 vector. All right, so hope you enjoy working on problems of that nature, and thank you.